I would like to invite Professor Shaji sir to deliver his keynote address. Before that, I would like to read his brief biodata for all our participants who have joined us across the globe. Professor Dr. Shaji is currently working as a professor of geology in the Department of Geology, University of Kerala, India. He also serves as director IQAC, University of Kerala. He was recognized in the Stanford Elsewhere top 2% scientist of the world according to the 2025 update in geology and geochemistry, geophysics, and one of his papers has received more than 1,000 citations. He was awarded his PhD from the University of Kerala in geology and obtained his master's degree with first rank from the same university. Prior to the university service, he worked as a professional hydrogeologist, scientist D in the Central Groundwater Board, Ministry of Water Resources, Government of India. He has 28 years of professional industry and teaching experience in geosciences with focus on hydrogeology and petrology. Five scholars took PhD with him and guided several MPhil and MSc theses. Currently, six research scholars work with him for PhD. He has more than 80 publications to his credit, out of which 50 are in international journals. He bagged Young Scientist Award from Kerala State Council for Science, Technology and Environment, Government of Kerala. He is the recipient of Best Associate Editor of Geoscience Frontiers by Elsewhere. He has edited four books with ISBN number. He has visited numerous countries as an invited speaker at many prestigious international conferences. Research interests are hydrogeology, water resource management, petrology, tectonics, and exploration geology. He also serves as associate editor for Geoscience Frontiers and Scientific Report. Sir, I would now like to invite you to deliver your keynote address on the topic Heavy Metals in Groundwater, a Hidden Threat to Health. Over to you, sir.
Is it visible?
Yes, sir, it is visible.
Okay. So thank you, Pratik, for the nice introduction and giving the overview of this particular conference. And also thank Professor Ravinde for inviting me to be here in this conference as a keynote speaker. So I welcome all the participants once again. So I will take half an hour for my lecture. You can ask me in the last if you have any doubts. So now I will be covering heavy metals in groundwater, a hidden threat to health. Okay, so let us see medical geology, right? So now it is a subject which is getting importance across the globe because it involves the geological processes, the geological materials, and the human health, and also its geospatial connect. Therefore, you will see this interlinking connectivity. That means the geology. That means in an area, for example, any continent, there is rocks. Okay, the rocks are made of minerals, and after the disintegration weathering process, you will get soil. Water is also exists there in the hydrosphere. You have volcanic emissions, you have earthquakes. So all geological materials and activity are one place, and its geospatial connectivity. I mean, whether the same geology may have, in different places, in different countries, in different state may have different geology, same type of. Huh? Any issue?
No, sir. Please continue.
Okay. So the geospatial analysis also very, very important. Okay. Then its effect on the then it's the toxicity or the benefits of these geology to the health. It can be good benefit and bad benefit as well. So, and its health effect. So if you take that combined together, you will get the medical geology. It involves medicine, geology, then the geography. Geography means in the geospatial connection I am talking about. So the students should understand that we are going to link the geology with the health of the human being as well as the people where they are located. Their geology, their climate, their food habits, their water, everything matters a lot. So this is very important. So therefore, geology plays a very significant role in the health of a human being. Earlier, we believed that we are contributing, the geologists are contributing to the economic development of a country. But
Sir,
yeah,
sir, I just want to ask something. Sir, have you shared your presentation yet?
yes.
Because, sir, we are able to see your Zoom window.
Oh, really?
Yeah, that is why I just thought I'll just confirm.
Okay.
Yeah,
So I will just see.
yeah, I thought like, before you start with the main talk, I should just let you know.
I will just share
Yes,
it.
yes.
Now it is saying,
Yes, sir. Now we can see.
is it saying now?
Yes, sir.
Oh, I'm
We're
sorry.
able to. Yes. Please continue, sir. Yeah.
So this is the one. Now you can see this slide.
Yes, sir. We can see now. Thank you.
Okay, so now this is the medical geology I was talking about. Okay, so this involves medicine. I already talked geology, then the geography. Geography in the geospatial connect I am talking about. So you can correlate these things. Then it comes the term medical geology. So medical geology now, why it is so important, the geology, the rocks, the soil, the water, and it goes to the biosphere. Therefore it matters a lot with regard to the health of a human being. So therefore, earlier what we thought was, we are contributing heavily on the mineral deposits, economic development of a country. Now we are contributing, we have some space in identifying certain diseases or certain health positive aspects in terms of medical geology. Now, if you look at this, the human health being in the outer circle, so there are, our health depends upon the water resources, the agriculture that from where we get the vegetables, the fisheries, and the livestock. Okay, so these are the things which we take in terms of our food and water. So these are getting from the hydrosphere, from the atmosphere, from the lithosphere. Lithosphere, I put it here, sediments and soils. Okay, so this there is an interconnectivity in all these spheres, and the elements are also moving from one sphere to another. There is another possibility is that this is called the natural mobilization. Now there is another possibility we have opened up. It's called technically enhanced mobilization. So we are industrialization and other processes, technological advancement has also contributed the mobilization of the elements into the system. So the geogenic contaminants can come into the system, and which in turn goes to the human body, etc. So therefore, these are all interconnected. You can see that this water resources, that means the water which we drink. The agriculture means the fruit products, vegetable, including vegetable we eat, and the fisheries we eat, and the livestock we eat. All, they are getting these elements from the earth only. That's what essentially I want to tell you. Then now, yesterday also we have seen the dust coming from the volcano happened at Ethiopia, even in Delhi also. So these dust storms occur several times a year, resulting in increased incidence of asthma and allergies in the Caribbean region. Similar the case with the Delhi also, in many parts of India also. So there is a growing evidence that this type of dust may also be able to mobilize a wide range of pathogens and microorganisms affecting human and animal health. So this is also another concern. Okay, it is not only directly from the rocks and weathering, but the dust carried away, carried by the winds from different parts of the world and accumulating in different places can also contribute a lot in terms of pathogens, microorganisms, etc. Then you have heard about sulfur fumaroles near a volcano. So this will also ultimately go to the soil, to the water, to the ecosystem, etc. So these are some of the photographs, and you can imagine how it is. There is a possibility of contaminants, as well as there is a positive aspect also. Some of the elements are very good for our human health also. That is also we should take into account. students, please don't think that medical geology is something which is harmful the health. No, the essential elements which are required for the body also contributed by the rocks, water, and foodstuff, etc. I will come to later that. So now there are you should understand that when you take a rock, for example, any type of rock, whether it is igneous, metamorphic, sedimentary, when you crush and powder it, you can get it chemistry, major element chemistry by doing XRF analysis, and trace elements you can do by ICP-MS analysis. So the trace elements in the rocks can move by weathering and leaching, and it can reach to the soil. Then it goes to the water also. In the water, trace elements can come from the air also. From the atmosphere also, the trace elements can come. Then these things together goes to the food stuff. That means crops, food, animals. Then it goes to the animals, I mean humans. Then the airborne dust, volcanic activity, pollution also can go to the human, the ecosystem. So this is the pathway through which the elements are mobilizing from the source to sink. That essentially I wanted to show you from this slide. Okay, so the trace elements exist in the rocks, trace elements exist in the atmosphere as well. So these two can come into the water, then to go to the food, then through water and food, it can come to the human intestine or inside the body. Now, you have to know a little bit about the groundwater extraction. So in India, after the technological advancement, India is now the #1 or maybe the largest consumer of groundwater in the world. Around 230 cubic kilometers we are extracting from the different aquifers. Okay, so now there are rigs. These are called rigs, which are used for constructing tube wells and bore wells, through which you can take the groundwater from the deeper aquifers. So nowadays the depth goes beyond 500 meters. There are rigs available for 700-meter drilling also. So earlier it was hand-driven drilling, but now it is all technologically advanced drilling. So therefore you can extract more groundwater. So therefore in places like Haryana, there are over exploitation. Haryana, Indo-Gangetic alluvium, and parts of Rajasthan, Gujarat, etc. You will find that lots of groundwater being extracted. So this is the map, the hydrogeological map of India. If you consider these blue patches, this is called the unconsolidated aquifer system. That's the Indo-Gangetic alluvium, which is the major groundwater reservoir of India. Okay, this aquifer system consists of unconsolidated sand, silt, gravels, and pebbles. Along the beaches, along the coastal tracts of the to west coast and east coast, you have such sediments. But the major portion comes here. Okay, so there are huge quantity of groundwater is being extracted from these blue region. They are called the Indo-Gangetic alluvium or the alluvial aquifer, one of the major groundwater reserves of India. The availability is huge, but there are huge extraction. So therefore, there are many quality issues coming up in these aquifers. I will come to that later. So next is the aquifer. You go down, you will see that in the Kerala, Tamil Nadu, and Orissa, this part, you will find a rock called high-grade metamorphic rocks like charnakites and chondrites. Why I am telling you that these rocks chemistry is different from the alluvial aquifer. So here also, mostly they take from the open wells and the bore wells. Okay, so the natural recharge is very low compared to the earlier aquifer which I have shown. So the chemistry of the groundwater which you are extracting from these zones are different from the aquifer unit which I have shown earlier. If you take a groundwater from here and from here and here, it will be different because the country rock is different, the lithology is different, its disintegration rate is different, weathering pattern is different, etc. Next is the basement granite gneiss. If you take, for example, Karnataka, Bangalore, that part, if you look at the middle central part of India and all, you have the basement granite gneiss. So these also, sometimes it's a productive aquifer, but nowadays there is a big issue of the sustainability of the bore wells drilled in these zones. Therefore, for example, Bangalore, there is a heavy dearth of groundwater in the area Bangalore, because the bore wells are not sustainable for 10 years or 15 years. Sometimes for the first 1 or 2 years, it may yield more water. Then you start pumping more or deepening the bore well. That will, invariably invite more trace elements into the system. So because of the rock water interaction. So the next major aquifer is called igneous aquifer. This is called the Deccan Traps, Deccan Trap basalt. Okay. Here also the top is the black cotton soil, and the sustainability of the well in this region also is very big issue. And the chemistry of the water which you are extracting from this region is also very different from the water which you are extracting from these zones and these zones. So what I am essentially trying to say that the quality, the concentration of the major trace elements are varying with respect to their aquifers. So now for the students' understanding, I'll tell you, in a water, if you take the chemistry, the major constituents are in the range of 1 to 1000 milligram per liter. That means parts per million, ppm. Okay, those elements are the major elements are sodium, calcium, magnesium, bicarbonate, sulfate, chloride, silica. So these are the major constituents if you do an analysis. Then there are secondary constituents. Their range comes from 0.01 to 10 milligram per liter. Okay, so the upper limit I am telling you. So that is iron, strontium, potassium, carbonate, nitrate, fluoride, and boron. So these are called the secondary constituents. Then minor constituents are 0.0001 to 0.1 milligram per liter. Beyond that may be harmful for the health. Okay, but within this range, it is good for the health as well. So the antimony, aluminum, arsenic, lead, lithium, manganese, etc. So these elements are very important for body one way or other, but its excess accumulation in the body creates problem. So then the fourth category is called the trace constituents. Generally, they are less than 0.001 milligram per liter. Okay, so in the ppb level, it is. Then beryllium, bismuth, all these. So all these elements you can determine from a water body, from a water, whether it is a surface water or groundwater, you can determine all these major, secondary, minor, and trace constituents. Then you can make an analysis whether the concentration concentrations are within the permissible limit of WHO or Bureau of Indian Standard. If it is over, then there is a concern. Otherwise, absolutely no problem. Then the land use and the activities potential to groundwater pollution, that also you should understand. So in the residential area also, we have unsewered sanitation, land stream discharge of sewage oxidation ponds. Then there are many leakages, etc. Then industrial and commercial, there are many issues with regard to industrial pollution, mining activity, mine drainage, discharge, process water, sludge lagoons, etc. Then the rural area, cultivation with agrochemicals, irrigation with wastewater, soil salinizations, livestock rearing, etc. Then the coastal area, you have saltwater intrusion. All these are the potential activities which can pose threat or it can create groundwater pollution. Then if you take the contaminants in that way, for example, if the water is rich in nitrate, more than 40 ppm, it can create a baby disease called blue baby disease. Then it is sometimes carcinogen, formation, eutrophication in the water bodies, excess nitrates. So the sources could be sewage, fertilizer, landfill, etc. Then the pathogens, that is a major concern in India in most of the parts. Okay, bacteria and viruses causing typhoid, cholera, etc. So the sewage, landfill, septic tank, livestock. Then trace metals. So toxic, the trace metals when they are excess in, for example, arsenic, cadmium, nickel, etc. You find that they are carcinogens. Okay, therefore excess accumulation in the body can create many problems. So it can be industrial, it can be mine discharge, it can be geogenic. Then inorganic constituents, high dissolved solid, water hardness, gastrointestinal issues can come. Inorganic constituents, if it is more, that means you have high TDS. So convert soft into hard water. So these are because of the salt, sulfate, chloride. There are two types of hardness. One is called temporary hardness. Other one is called permanent hardness. If the hardness is going on boiling, that means the anions are carbonates and bicarbonates. If it is not going, it means the anions are chloride or sulfate, etc. That you should understand. So the difference between permanent hardness and temporary hardness is also important. Then the organic compounds like volatile, semi-volatile compound, organics, petroleum derivatives, PCBs, and pesticides also creates problem. Then the salinity, if you look at in many West Coast, East Coast, we have the salinity issue. Some in Rajasthan and all, we have inland salinity, not directly from the sea. And fluoride, it is reported in 22 states from India, nitrate almost all states, arsenic in 20 states, iron and manganese mostly in West Bengal, Tamil Nadu, Orissa, UP, Bihar, Kerala, etc. Uranium, radon, strontium. Now uranium is a big issue now in India. So the Andhra Pradesh, Himachal Pradesh, etc. Even from the Bihar, I will show you that report of uranium contamination, chromium in Orissa, selenium, Himachal Pradesh and Punjab, then few toxic elements, because very few studies are available on the toxic metals in the groundwater system. So our study, even in my study, we have reported that, in various elements, trace elements like arsenic to aluminum, all these elements are present in the groundwater. So some of the elements are called toxic metals. They are called lead and arsenic. Some of them are alkaline earth metals. They are strontium and barium. They are also reported in many aquifer systems. Then the transition metals, they are called, example, manganese, cobalt, and nickel. Then the metallic elements, copper, cadmium, iron, zinc, and chromium. Non-metallic elements, boron, selenium, aluminum. So all these elements can be determined using the ICP-MS, inductive coupled plasma mass spectrometer. For example, ICP-MS and QICP-MS. So these instruments can be used to determine the concentrations of these toxic metals, alkaline earth metals, transition metals, metallic elements, and non-metallic elements. So students are able to distinguish between these elements, because in the examination point of view, these are very, very important. Which are the toxic metal, which are the alkaline earth metals, what are transition metals, metallic elements, and non-metallic elements which can be present in the groundwater system. So the cadmium, these are the, there is no relaxation in the cadmium, for example, and the co-contaminant along with cadmium, you can have chromium, manganese, lead, molybdenum, tin, lead, etc. Then the rock water interaction is the main source, then coal, then cadmium sulfate also can be contributing, mining industries, landfill, etc. And arsenic, no relaxation, 0.01 ppb. So iron, along with arsenic, you can have iron, tin, lead, silicon, zinc, manganese. So the source is orpiment and arsenopyrite sediments. Mostly the arsenic are derived from the sediments. Arsenic is to the groundwater system is derived from the sedimentary aquifers. Okay. So this is about chromium. It's from the chromite. Okay. Mercury is a mercury sulfide. Iron can come from hematite, magnetite, and other iron ores. Even in the laterite also can contribute to some of the ferruginous sandstone also can contribute iron to the system. And the limits are given here. And if you look at the groundwater quality issues in India, it is the overall increase in the salinity, presence of high concentration of fluoride, nitrate, iron, arsenic, uranium, total hardness, toxic metals, and biological contamination. So this is the one paper I have published. I told you this paper has received more than 1,000 citations. So arsenic contamination of groundwater. Actually, it is one of the major concerns in the world now. And what I found in my literature review that the arsenic is more in the sediments derived from the younger orogenic belts. For example, in the Himalaya, in the Indo-Gangetic alluvium, so we have more arsenic along this line. Okay, so that means all over the world, if you look at that, the present younger orogenic belts, very close to that, you have a concentration of high arsenic. That means in the sedimentary aquifers. And India, around 50 million people are currently at risk in the arsenic. So you can see the arsenic contamination is in this belt mostly. And we have occurrences in other parts as well. But along this line, you have more arsenic reports in the aquifer system. So in Karnataka also, it is not from the sediments, but all these sources are sedimentary aquifers. Whereas in the Karnataka, the arsenic is reported from the arsenopyrite in the gold mineralized zones in the Yadgir districts, etc., Raichur, and in the Chhattisgarh also in the acid volcanic rocks of the Kotri lineament, we are getting the arsenic in the groundwater system. So another important aspect I have studied is the fluoride contamination. So many parts of India, we have the dental fluorosis and the skeletal fluorosis. And also, if you look at the fluoride is actually derived from the hard rock, not from the sedimentary aquifers. All are derived from the hard rock. And also the climate also a major factor. So most of the fluoride affected regions located in the subtropical to tropical climate regions. You can see here, the tropical and subtropical climate regions are more affected in fluoride in the groundwater system. The fluoride bearing rocks, if you look at this is the granites giving more fluoride bearing rocks. They are more Rapakavi granites, alkali rhyolite, phonolites, some gabbros, or most of these rocks are contributing fluoride into the system when it is disintegrated by weathering. So these are the fluoride affected regions. You can see all across the India we have fluoride problems. Okay, and next problem is the uranium problem. If we look at that in groundwater, the uranium is reported from this much places. It's a radioactive 238, uranium 238. So if this is the state in which the uranium is detected almost, but in Kerala there is nothing. Jammu and Kashmir, no. Himachal Pradesh. So these are wherever you have the red lines, that means there are uranium reports in the groundwater system. So the other day, 2 days back, there was a report that uranium found in breast milk of lactating mothers across Bihar. More studies expected in other states also. Now these medical doctors involved into it, they said they would like to interact with the geologist also, hydrogeologist also, to locate the source. Because if you see, this is the uranium 238, they have detected even from the breast milk. That means the source we have to take, and we have to identify how it has come to even to the breastfeed milk also. So there is a report of the groundwater system, but these are the situations now prevailing in our country. So the Central Groundwater Board monitors groundwater quality across India, even State Groundwater Department as well. So several studies reveal that the trace elements are increasing in the groundwater system. So the contaminants include arsenic, uranium, lead, cadmium, chromium, and other heavy metals. Okay, 2021 data shows that around 36,000 rural habitations across the India are affected by these heavy metals. So in the Punjab, Malwa belt contamination, arsenic contamination is detected, lead contamination is detected, cadmium contamination is detected, chromium contamination is detected, uranium contamination is detected. So these are the state-wise observations. Punjab has significantly high heavy metal contamination. Haryana shows arsenic, lead, cadmium. Uttar Pradesh, Bihar, Assam are heavily affected by arsenic. Maharashtra, there are high lead contamination. Tamil Nadu showed contamination of all the categories, including chromium. Delhi shows multi-metal contamination, lead, cadmium, strontium, and some states have less reports also. So these are the habitations or number of people affected. So Rajasthan has the largest number of contaminated rural habitations driven by salinity and fluoride. Assam, Odisha, West Bengal show extremely high iron concentration. Arsenic contamination heavily concentrated in West Bengal, Punjab, reflecting well-known hotspot regions. Nitrate issues are notable in Rajasthan, likely due to agricultural activity and groundwater over extraction. So these are the health impacts. When if it is increasing the arsenic, it can lead to the gallbladder issue, stones, and then mostly in many places the gallbladder removal is a common one. If you ask the hospital data, the lung disease, prostate cancer, as well as the cardiovascular and neurological issues, cadmium associated with the cardiovascular disease, skeletal damage, etc. Lead, particularly harmful to fetal embryonic development, can cause anemia. Mercury is also linked to autoimmune disease. Antimony contributes to the development of cardiovascular disease, and the fluoride, the dental fluorosis, skeletal fluorosis, etc. So the process is bioaccumulation. That means heavy metals are not easily degraded. Therefore, it can accumulate in the body tissue over a time. So when it enters the body, it is very difficult to flush out. That just like any other major constituents. So even from the low-level exposure can and increase the bioaccumulation. So then another process is called biomagnification. Another one is called oxidative stress. Mental toxicity can cause the production of free radicals which damage DNA and other cellular components. So the metal toxicity always a matter of health concern. If it is in a permissible limit, there is no issue. If it is more, there are processes. So the contamination is both anthropogenic and geogenic. So this is, if you look at that, in the atmosphere, normally when the rainfall, it is the electrical conductivity is less than 50 microsiemens, and chloride may be less than 5. So this is normally bicarbonate water. When it touches the soil, it becomes calcium bicarbonate water. So that means when you take immediately from the top soil, the groundwater will be calcium bicarbonate. When you go down, it takes in different actions like dissolution, precipitation, evaporation, mixing, etc. Then you go further down, you will get ion exchange, redox reaction, sorption. Very close to the water table, these things are happening. That's called ion exchange reactions, rock-water interactions, redox reactions, sorptions, etc. Then further, if you go down to the water table, you will have dissolution, precipitation, ion exchange, redox reactions, mixing, gas generation, consumption, etc. What happens? These calcium bicarbonate water becomes calcium or magnesium or sodium. So the cation will change from calcium to sodium when you go down, and the bicarbonate will change to chloride. So these are the hydrochemical phase change happening with the interaction at different spheres. So the trace elements are also is more likely to be added below the groundwater table. So therefore, when you are doing some disturbance below the groundwater table, you can expect the more rock water interaction and contribution of the toxic elements into the groundwater system. So earlier we used to take the dug wells for the groundwater. Nowadays we are using the bore wells. So it is more deeper and more trace elements and the toxic elements concentration can exist in this water than this one. So this is a shallow level. So earlier, this we used to conserve the Vado zone where the pore spaces are filled with water, air, and below you have the pore spaces are filled with water. So the boundary is called water table. When you take a well, you'll find the water level. This is called the water table. What happens nowadays? You are removing the Vado zone. You can see in this picture. You are simply removing for the construction purpose. Actually, we are destroying an aquifer. So when you are removing it, what happens? You are directly going to a zone where the saturation zone, where you are triggering the reaction more. So the water become acidic. You are generating more reactions that can ultimately contribute to the release of trace elements into the groundwater system. Now you see that this is the way in which the groundwater is leaking because of the topsoil removal. You can see that the groundwater is leaking. And why I am saying that these are different. This is a particular chondrolite, and when you drill a borewell here, the chemistry will be different. This is a charnockite. When you drill a borewell here, the chemistry of the groundwater will be different. This is a ultramorphic rock. This is called tall tremolite schist. When you drill a borehole here, you will get a different chemistry for your groundwater. Here, there are some contact zones. Okay, when you drill in the contact zone, the chemistry will be different. So the aquifer is not uniform throughout the country. It is heterogeneous. Therefore, you can expect different chemistry also. So this is a peridotite with magnesite veins. Magnesium will be more. Suppose if you put a borehole here, the water will have a chemistry of more magnesium because magnesite is there. So these understanding should be very clear. Otherwise, you will wonder how these trace elements are coming into the system. So in my well, there is no trace element excess, but in other well it is there because the underground, the aquifer is not homogeneous, it is not isotropic, it is heterogeneous. Therefore, you can expect different elemental concentration at different geospatially located regions. This is another rock. So now you see, when it is interacting the whole rock, the rainfall, it goes through. These are called the secondary porosity. These are called the rock water interactions, and the chemistry can slowly change while the water passes through these deep fractures. So now this is the one which you can normally see that this is a top aquifer. But this aquifer layer, when you closely look at, there are certain clay layers are there. These clay layers used to act as a filter point. This is a natural filter. Any heavy metals or the anthropogenic contamination, this can filter it out. But these days we are removing all these things in the natural systems, and the surface water is almost contaminated. This can also contribute to the groundwater system. You can see these are the pictures, and even some of the bore wells which you see in your village, they are rusted and in a dilapidated manner. This also contributes contaminant into the groundwater system, and even in the water tanks which you are supplying are also very old and it may not be properly cleaning. This also contributes some elements into the water system, and therefore we have to compare these are the hard rock, this is the top layer. So there are many petrologists work, they have many data on the geochemistry of the rocks, but you have to compare the geochemistry of the water also, then only you will understand the process. So I have published a paper, Characterization of Trace and Heavy Metals in Groundwater, a case study from the tropical river basin of southern India. One of my research scholars has published this one. So we found that the barium is more in the groundwater system, and this is another concept, the aquifer desaturation. That means development means the groundwater level is going down in the cities. So this also can add with the industrial effluents or the domestic effluents. This can also contribute contaminants into the system. So then another interesting study we have conducted is that myself and Dr. Sudhir of the Srijitra Tirunal Medical Science and Technology Trivandrum, we have a joint paper called The Quest for Geo-Environmental Factor for Moya Angiopathy. Is arsenic the elusive environmental agent? That means the arsenic, whether the arsenic is contributing a disease called myoma, it is a neuropathy disease. So he was asking me for a joint study. Then we could establish that the arsenic in the groundwater or the drinking water can act as an agent for a disease called Moya angiopathy. So this is pure medical geology. So this you can see Department of Geology, me and the Department of Neurosurgery, Srijitra Institute, we are collaborating. So this is the real sense of medical geology. And iron is another important issue because there is a shortage of time. I just passed through. So I have collected the iron, just like the rust, from the water bodies. I have prepared a paper called hematite nanomaterial. These materials, which are from the small ponds and the nalas, there are rust iron material. So if you collect it, I found it is a very useful material. It is a nanomaterial. It's called hematite. So there are some useful things also you can find out. So medical geology today is focused on the prevention and minimization of geological risk posed to public health. In support of this primary objective, a number of common goals exist in the medical geology field. One is identification of harmful geochemical anomalies such as toxic or deficient element levels in water and geosystem, Identification of health benefits, that's also medical geology. Identification of health benefits, risk of geological materials and processes, promotion of public awareness of geological health hazard and how to mitigate them. So my recommendations in the keynote is medical geology should be included in the geology curriculum of the 4-year undergraduate program as well as master's program. Create a digital database platform for groundwater and its trace element quality. Develop a software to correlate geochemistry of rocks, groundwater hydrochemistry, and health effects. To study climate change impact on groundwater chemistry. Propose new innovative methods to purify water and to facilitate selective absorption. You should not absorb everything. If you want to remove arsenic, only arsenic should be removed, not other beneficial elements should not be removed. So facilitate selective absorption and AI-based, artificial intelligence-based water filtration. These are my recommendations. Thank you for the patient hearing. I know I have taken a little more time, but my special thanks goes to Professor Kritikumar Ravinde and Pratik Goat for facilitating these events. And thank you so much. Thank you once again.
Thank you so much, sir. It was a wonderful lecture. I'm sure our participants have got a good detailed idea about the subject, medical geology. I would now request the participants if they have any questions to ask to Professor Shaji sir, they can ask.
Yeah, you are free to ask anything, any simple doubt you can ask, no issues. The chair would like to comment something, chair. Hi. And what's up?
Sir, a wonderful lecture, sir. So many new things we learned from you. Always, always a pleasure to listen to you.
Yeah, thank you. Any
Because of his
students or
professional background at CGWB and now academic blend, it is an excellent talk, sir. So
yeah,
nice information. It is a
yeah,
blend
yeah,
with your experience with research.
yeah. That's what our 11 years of experience in Central Groundwater Board contributed a lot.
Yes.
So there is a blend of academy and industry or professional organization. Students, you would like to ask me anything, or you are all understood, or you have not understood anything?
That's the problem.
It can be both. I mean, both way. I mean, fully
No,
understood.
this time it is that they seems to have understood the things,
Okay.
and that curiosity has generated in them. You are doing really good work. Some question is there.
Yeah.
Yes, sir, I would like to read it out. There is this one question by Akhila, and she's asking, "Hi, sir. There was an image you showed and told that clay layer would be acting as a natural filter, removing heavy metal. But is the clay layer not impervious of water flow?"
Yeah, that's a very good question. Normally what happens, this clay layer is, I don't know whether I can, this clay layer is not a continuous clay, it is a dismembered clay layer. That means it is an acute tad. So that clay will have some sand also. You understand? So there is a difference between aciclude and acutad. Acutad means you will have little more silt, sand in the clay. So the maybe around 70% clay, if you take a textural analysis, you will find that 20% of sand, 10% of silt. So this is a very good filter that is created by nature. We should understand that in every system, a laterite aquifer system at the bottom, you will have that layer that will act as a natural filter. Hope it's clear, right? Just imagine, you read about acutad.
We hope. Yes, sir. She's saying thank you.
Okay, fine.
Do we
Anything
have
else?
do we have any other question from our audiences?
Hello, sir.
Yeah. I can hear, no issues. No
Hello.
worries.
Yes, I wanted to ask about how do you combine the hydrogeological and medical geological research?
Me. Yeah, because, I have been working in the Central Groundwater Board from 1997 onwards. So I was wondering in some area, some people are affected by certain diseases. So my curiosity went on like that, any linkage between the water resources. The groundwater normally, depends upon the aquifer. So aquifer is nothing but a geological formation which can yield and store water. So when it is storing, it can have an interaction with the surrounding aquifer material. So that aquifer material chemistry can contribute into the water. So when you take the water as a drinking water, so your nutrients are supplied by water and food. So there is a direct linkage. That means the disease. So we are not treating it. We can find out some sources why that particular area is affected by certain diseases. That has created a curiosity. Then I have started linking. You can also think of like that. Okay.
Sir, we have one more question in the chat box. Is
Yep.
there any possibility of contamination from trace element air pollutants reaching groundwater?
Yeah. I mean, it is actually, what is the system? It is the groundwater in the top layer. It is called a dynamic system. Dynamic means the groundwater is getting recharged from the rainfall. So whatever atmospheric phenomena, it is directly linked. Okay. So if it is a dust storm, then suddenly there is a rainfall. So it can go down to the groundwater and it can add the groundwater system. So not deep aquifers, but in the phreatic aquifer, you can expect such sort of a contamination.
Thank you so much, sir. Do we have any other question?
I think I have taken more time. You can maybe.
Yes, sir.
Thanks.
Sir, it was a pleasure.
Yeah, I mean, you have done a wonderful job, Pratik, and I appreciate your effort.
Thank you,
Professor, anyway, you have a good student like Pratik. Very nice.
Yes, very proud.
Very happy.
And the team behind him is also equally very good.
Yeah, and
So
all
you
other
can, yeah.
other people who are involved in it, I appreciate all of them. Thank you so much.
Uh,
Thank you, sir. It was a pleasure listening to you.